Have you ever just stopped for a second to think about the absolute magic that's happening all around us right now? I mean, data is literally flying through the air, connecting your phone, your laptop, probably even your watch, to this massive global network. It's this unseen revolution that has totally reshaped our world. We're talking about everything from cellular systems with billions of users to the Wi-Fi humming away in our homes. This tech is fundamental. So, in this explainer, we're going to pull back the curtain and really see how it all works.
It seems like a pretty simple question, right? But the answer, well, the answer is a story of incredible human ingenuity that spans centuries. How do we actually take a voice or a video or an email and send it invisibly across a room or a city or even an entire continent? That's the mystery we're going to unravel. We're going to trace the whole path, from the most ancient signals all the way to the high-speed networks we can't live without today.
All right, so our journey starts way, way before the internet, before even electricity. See, the dream of communicating without being physically tied down by a wire is a really old one, and the road to our modern wireless world is just paved with these fascinating breakthroughs, each one building on the one that came before.
This timeline really puts the acceleration of progress into perspective. For thousands of years, we were stuck with line-of-sight communication. Things like smoke signals that had to be relayed from one hilltop to the next. Then, boom, 1895. This is a massive leap. Marconi demonstrates the first real radio transmission, pushing a signal over 18 miles. Just like that, radio was born. The next huge jump doesn't happen until 1971, with a network in Hawaii called AlohaNet. It used something called packet radio to connect computers across different islands. The game-changing idea here was breaking data into little packets, a concept that laid the essential groundwork for the internet. And that innovation leads directly to the 1980s and the very first cellular systems, which brought wireless voice calls to the public for the very first time.
And what an explosion it has been. It's actually hard to wrap your head around the scale of it. Those early mobile phone systems, they were incredibly limited. Get this, 30 years after mobile service was first introduced, the entire system for New York City could only support 543 users. Just stop and think about that. 543 people in a city of millions. Fast forward to today, and there are about 2 billion cellular users worldwide. It is without a doubt the single most successful application of wireless networking in history. It went from a wild luxury for a tiny few to an absolutely essential tool for billions of us.
So, all of this incredible success, it just fuels an even more ambitious dream. We call it the wireless vision. And it's not just about phones anymore, not by a long shot. The goal now is seamless, untethered connectivity for a huge range of applications, creating a world where information and control are always right at our fingertips, no matter where we are.
So what does this grand vision actually look like in practice? Well, it's everything you see here, and a whole lot more. Of course, we expect perfect voice calls and blazing fast internet. That's a given. But we also demand buttery-smooth video conferencing, instant file transfers, and messaging. But the vision goes even further. We're talking about vast networks of remote sensors that monitor our environment, or control systems for things like automated factories or even smart highways. Basically, we want it all. And we expect it to just work, seamlessly.
But here's the catch. And this is really the core challenge of designing wireless systems. Not all of these applications are created equal. As you can see in this table, a simple voice call, it doesn't need a lot of data, but it's super sensitive to delay. Any more than about 100 milliseconds, and our brains start to notice that awkward lag. But it can handle a pretty high bit error rate, or BER. That just means a few bits of data can get messed up, and our brains are so good they just fill in the gaps we don't even notice. Downloading a web page, though? Totally the opposite. It needs a huge data rate and an extremely low error rate. You can't have a single bit out of place, but we're okay waiting an extra second or two for it to load. And real-time video is the toughest of all, right? It needs both high data rates and low delay. Trying to build one single system that can perfectly handle all these conflicting demands, well, that's a massive engineering puzzle.
And this brings us right to the heart of the problem. That big, beautiful dream of everything, everywhere connectivity runs headfirst into the hard physics of the real world. The wireless channel, which is really just the air all around us, is a fundamentally unpredictable and frankly difficult medium for communication.
To really understand just how difficult this is, let's start with the one thing we absolutely can't make more of, the radio spectrum. This is the range of frequencies we use to send all our wireless signals. It's a finite natural resource, and it is unbelievably valuable. In the European auctions for the spectrum needed for 3G cellular networks, companies spent around $100 billion. And get this, that wasn't for towers or hardware or any equipment.
That was just for the license to use a slice of the air. That staggering cost tells you everything you need to know. Spectrum is the single scarcest, most precious resource in the entire wireless world.
And believe it or not, that's just the beginning. Beyond the insane cost of spectrum, engineers have to deal with a whole list of other physical hurdles. Signal power naturally gets weaker and weaker the farther it travels. The channel itself is constantly changing because of obstacles and interference, which makes it super unpredictable. Our devices have to be small and light, which forces them to run on just sips of power from tiny batteries. And then, on top of all that, these wireless networks have to somehow connect seamlessly to the super high-speed wired internet, which is a whole other complicated problem in itself.
So how did engineers even begin to tackle this mess of unpredictability? Well, they had to come up with a completely new design philosophy. You see, traditional wired networks are designed in these really rigid layers, where each part does its own job in total isolation. It's simple, but in the chaotic world of wireless, it's terribly inefficient. So the solution was a radical idea called cross-layer design. It basically means making all the different layers talk to each other. The application you're using needs to know what the physical connection is like at that exact moment. The network routing needs to adapt based on what that application is trying to do. It's a completely integrated, adaptive approach that is absolutely essential for getting high performance in such a difficult environment.
So given all of these challenges, how did we end up with the incredible wireless world we have today? Well, the answer wasn't one single magical system. Instead, it was a whole ecosystem of different solutions, with each one specifically tailored to solve a certain part of the puzzle. Let's break down the main systems you're probably using every single day.
First up, the absolute powerhouse cellular systems. Their core genius is a brilliantly simple concept called frequency reuse. Since that radio spectrum is so precious and scarce, a cellular network carves a huge area up into smaller zones or cells. Frequencies that are used in one cell can then be reused in another cell that's far enough away without causing too much interference. This one simple idea is what lets the network scale up to serve millions of people in a city using just a tiny slice of spectrum.
Next is the system most of us are probably using right this second: wireless LANs, or as we all know it, Wi-Fi. Now, instead of covering an entire country, Wi-Fi is designed for high-speed data in smaller, local areas. And crucially, it often operates in unlicensed frequency bands. This means companies don't have to pay billions of dollars for a license to use them. This dramatically lowers the cost and is the reason Wi-Fi has become the go-to way to get online at home, at the office, or on campus.
Okay, now let's zoom in even closer. We've got personal area networks like Bluetooth and Zigbee. These guys aren't about crazy high speeds or long range. Their entire design is optimized for one thing and one thing only: connecting nearby devices using as little power as humanly possible. This intense focus on low cost and low power is what lets us have wireless headphones, keyboards, and smart home sensors that can run for months or even years on a tiny little battery.
And finally, let's look up. Satellite networks solve a problem that no ground-based system ever could: true global coverage. By beaming signals down from space, they can provide connectivity to ships in the middle of the ocean, planes high up in the sky, and remote areas where it's just impossible or way too expensive to build cell towers. They fill in all the gaps, making a truly global network a reality. So what this really shows us is that there is no single best wireless system. Each one, cellular, Wi-Fi, Bluetooth, satellite, represents a different set of choices and compromises. The entire field is defined by this constant balancing act, this series of fundamental trade-offs that engineers have to navigate every single day.
And that brings us to the ultimate trade-off. Let's just be really clear about this. When it comes to pure performance, wireless just can't compete with a wired connection like a fiber optic cable. Wires offer mind-blowing speed and rock-solid reliability. But they're fixed in place. Wireless trades some of that raw power for something that wired networks can never, ever offer: complete freedom, mobility, and convenience. We choose wireless not because it's technically better, but because it sets us free.
And that brings us right up to where we are today. Because as powerful as our current systems are, the wireless revolution is far from over. As the source material for this explainer puts it, the gap between current systems and the vision for future wireless indicates that much work remains. In other words, the demands for things like smart cities, self-driving cars, and the Internet of Everything are constantly pushing the boundaries of what's possible. The work of inventing the future of wireless is happening right now.
So this leaves us with the central, multi-billion-dollar question for the next generation of wireless innovation. We're adding billions and billions of new devices to the network, everything from our cars to our coffee makers, but we are not getting any more of that precious radio spectrum.
So how do we fit an ever-expanding digital world into the same finite amount of space? The answer is going to require even more cleverness, more efficiency, and maybe entirely new ways of thinking about how we share the airwaves.
If you enjoyed this deep dive into the world of wireless, do us a favor and hit that like button. It really does help other people discover our work. And of course, make sure you subscribe and turn on notifications so you don't miss our next one. We'd also love to hear from you, so if you have any questions or if there's some other complex topic you want us to break down next, just let us know in the comments below. Thanks so much for watching.